Okay, and we're live. Welcome everybody to the first audio programmer meetup of 2025. My name is Josh. I'm the founder of the Audio Programmer, and I'm joined here with some great colleagues from the world of audio programming, and we're going to talk about some awesome new ways that you can create your own audio products, plugins, and so on. So first off, we have Alexander Propachuk, Sasha Talashov. Please correct me if I've pronounced that wrong. And Steve
All
Atkinson.
good.
So they're from the GPU audio team, and also they've teamed up recently with Steve Atkinson, who is the creator of the neural amp modeler, who that you may have heard of before. Um, so that's a very well-known open source project that creates models of guitar amplifiers and pedals with state-of-the-art accuracy. So taking a dive into the world of AI today and leveraged with the power of the GPU. And then we're going to talk about new ways that you can prototype audio. So one of the things, if you're programming with C++, is that you know that getting started and getting sounds up and running quickly is a challenge. And Domenico Cipriani from Italy is here with us to talk a little bit about Fausto, which is his environment for rapid prototyping for audio. Before we get started, I just wanted to say thank you to our sponsors, Focusrite and JetBrains, for sponsoring the Audio Programmer Meetup. Without you, this wouldn't be possible. Another note that I wanted to make is that there have been many people in our community that have been affected by the fires that have been happening in LA. So we're very conscious of what's going on out there. We've taken a look around to look at different types of charities and different types of ways that we can help support this effort. And the one that we've found that seems to work the best is called Music Cares. So it's supporting the LA uh, professional music community. And what I'll do is I'll just share my screen very quickly just to show the website very quickly. And so this is where we're going to give. We don't. I've been trying to think of some really interesting ways that we could help support the community and to give more. But this is the best one that I can think of at the moment, is just to help support through this charity. And so I invite you to give as well, or to give to a to a place that you support or that resonates with what you're doing. Since this is for the music community in Los Angeles, I thought that this resonated really well with what we're doing uh, at the Audio Programmer. So please support the effort. We have people in our community that are being directly affected by by what's happening there in LA. Also, we have NAMM next week as well, so we're just trying to find ways to help support. So we invite you to do that. Now I've just got to figure out how to stop sharing the screen. Oh, there we go. Cool. So without further delay, let's go ahead and just jump into our first talk. So this is coming from the GPU audio team in collaboration with Steve Atkinson. And the title of the talk is GPU powered neural amp modeler, high performance inference for real-time sound processing. And this is a description of the talk. There is a large market of audio processors which utilize machine learning as of today. GPUs are widely used for training neural network models, but most, if not all, real-time inferencing for audio applications is still done on the CPU. Using Neural Amp Modeler plugin, we present the possibility of doing real-time inferencing on GPUs utilizing GPU Audio's platform. And without further delay, I will pass it over to the GPU audio team with Steve Atkinson. Take it from here.
Thanks, Josh. Well, first of all, let introduce ourselves. I'm Sasha. I'm co-founder of GPU Audio. We also have our CTO, Alexander, here, and Stephen Atkinson, the original author of Neural Amp Modeler. Let me just start with a part of the story, how we came up with this collaboration. So that was one part of the random story. So we've been thinking about our participation, I mean, GPO Audio's participation at ADC in Bristol last year in November. And we've been looking for picking up some open source project that we can empower using our SDK that we wanted to release this year, early this year, as we promised. And there were so many options to what to do using GPUs. And just because the guitar instrument was always a passion of most part of the team at GPU Audio. And I also heard the other proposals, and it just came natural to pick up Neural Amp Modeler as a project of our choice. And at the moment that we've been picking this project up, we didn't know what it's made of. I mean, internally, the dependencies, the stack, how it actually worked. We didn't know the interfaces it utilizes just to bridge with the DAW, what the model itself is made of, or what are the different implementations of LSTM, WaveNet, and CNNs. We didn't know anything about it. We don't know even the linear algebra behind that thing before we pick it up. So that tells to the audience that the fact that it was a really good choice. And it took only 3 weeks, as I mentioned during the ADC or the Developers Conference, where we originally presented our talk, our workshop, how to exactly port this open source project utilizing our SDK. And it just took 3 weeks, which is extremely fast. Like it is almost as fast as you write code itself, right? And by the time we've been picking this project up, then we originally contacted the author, Steven. And I just want to pass my word to Steven to tell to the audience a little bit more about how he came with the idea of Neural Amp Modeler and how it basically works in general. And then we will speak about the GPU implementation. Thank you. Steven?
Yeah, sure. Thanks, Sasha. Yeah, like you said, just from my perspective, this kind of neural amp modeler project, it's one of the really kind of cool things that it's been able to do, and I'm really thankful for is, that it's been able to, find its way in front of folks like Sasha and many others at this point so that they can kind of have a go at it and kind of build some cool stuff. So Sasha had asked me to give maybe just like a little bit of background from my perspective and sort of like tell folks a little bit of a story about like how it got to where it is. So I've got a couple notes for myself here, and I guess I'll kind of start from kind of the beginning of this thread. So a lot of folks might not know this, but Neural App Modeler has been a thing that has been around since basically about the end of 2018 is when I first had the idea. And, since it's an open source project on GitHub, you can go back and you can see kind of like the first public commits. I think it's like on January 1st of 2019. So you can tell what I was doing after celebrating the new year. Um, but yeah, like at that point, the way that I got into this is that, I have, kind of a background in using computer programming and simulation, kind of for physical applications. I was studying like, material science in school. And after I had graduated and got my degrees, you know, it was kind of at that point in the mid 2010s where, machine learning, deep learning was starting to do some really cool stuff. The one that really kind of stood out to me was that, if you had a smartphone, that you could talk at it and it could recognize what you were saying. And the fact that this stuff like all worked really well, really kind of fascinated me because, if you think like to like earlier days where people had these little computer programs you could install with like a CD, and they were like, oh, you can talk in a microphone and we'll write text for you. They didn't work really well. So, things were like really changing, and like all of a sudden there were these kind of suggestions of like some like really cool, capable tech, and that got me really interested in it. So I had started, working in machine learning, applying it to kind of modeling like engineering systems. And, as a sidebar, as an electric guitarist, I was kind of looking for, a kind of hobby project to kind of combine this stuff that I was working on and this hobby of playing electric guitar. And so I had used like kind of like digital gear a lot in my past, and it just kind of occurred to me like, yeah, can we try and use like a neural network to, make this like input output, sort of function that my amps over here are doing. So, a neural amp modeler, hence the name. You could probably write it with lowercase, but that was kind of the idea. And since I was kind of doing it to with the intent originally to kind of test my comprehension and what I had learned, I basically did it closed book. I was like, okay, given what I know about deep learning and stuff so far, how would I approach this if I didn't, know anything from other folks? So, the first couple of years of it were just kind of like, based on my intuition, kind of building these sorts of things. And it looked kind of cool. I made like a little video, a couple of my friends saw, and they're like, "Hey, that's cool." And that was about it for a few years. I kind of put it on the shelf, did some other stuff. Um, but it kind of got a second wind around 2022 is when I think the right people on the internet found it. There were a couple like tech savvy, guitarists, and I think I just remember seeing like someone on like a forum mention it and like link to, the repository, and I was like, this thing was just kind of hanging out in my corner of the internet. It's really kind of shocking what people can find as they go looking around. But I could kind of see it getting shared around, and people were kind of getting really excited about it. And so it was kind of this combination of like, the right people that were really just kind of like shouting from the rooftops about how much fun they were having, kind of using the tech. And, that kind of encouraged me to sit down, take it a little bit more seriously, polish up some of the code, and try and help make the whole picture make sense about just like how do you get from training a model to, putting it in a plugin and all. And, kind of the focus was for a fair amount of time, just like making this, make sense to folks who didn't have, that sort of background. And so, building little tools like, okay, if you just kind of log on to this website, you can press a few buttons as long as you can reamp a file, and, hopefully trust the process, look at the little picture at the end and see that the waveforms look about the same and get excited. But yeah, like that kind of from that moment, like 2022 onward towards, kind of today, it's been a combination of, sort of refining the stuff that's in the open source code. It's, found its way to a much larger user base, and I've found out all sorts of things that break when you have that many different people and different computers trying to use it. So kind of trying to patch those things, but all the while, this is an open source project, right? So one of the things that I think is like a really cool opportunity here is that I'm not going at this kind of like someone who is, trying to like build like a product myself, but I'm looking at this kind of as the tech that it is and saying that, if there are people out there that have cool ideas, like how to kind of like wrap this together and sort of like, make something that hits in kind of a fascinating new way. I've gotten, the chance to talk with all sorts of people who have had really fascinating ideas about what you can do from a product perspective. So that's the part that's been, a really rewarding experience, I've got to say. So, we kind of fast forward to this last year, 2024. As I was kind of going back through the notes, I think we had product launches from 8 different companies in the last year. The open source repositories had 18 different like releases on the, different repositories for training and the inferencing and this kind of demo plugin, neural amp modeler plugin. It's named really, really imaginatively. And yeah, I'm just really thrilled with where it's ended up, and folks like Sasha who have kind of sat down with it, and you guys definitely did your homework, as I saw it was with your ADC presentation, and yeah, that's just like super thrilling to me. So like Sasha, GPU audio, if folks out there are kind of watching this and you're a builder and you've been thinking about how maybe you want to do something with this, I would definitely recommend that, have a look at the code. It's all open source. It's very favorably licensed. And get in touch with me if you've got some questions. There's a website, neuralampmodeler.com, and there's some contact info on there. So again, if you're thinking about building stuff, then definitely get in touch and I'd be happy to chat. But that's kind of my thing. So
Thanks, Steve. So Josh and everyone here in the room and the audience, we just wanted to share the whole thing once again. The GPU-powered implementation of the neural app modeler, how exactly came with the idea, and what we offer to the community. So the number one thing, Josh, did you want to say something?
Yep, I'm all good.
Okay, cool. Yeah, so first of all, as Steven mentioned, there are many participants, companies that utilize, and individuals that utilize Neural Amp Modeler for their own products, and starting with Mododia, PolFX, Tone Hunt, and Tonocracy, and some other companies, we wanted to bring GPUs to this space because of two reasons. One reason that is not there yet, but we also hope to bring something in regards to that functionality. We want to speed up the training of the models. We want to enable this not just from like your GPUs of your home setup, but imagine if you have this as a tiny portable device that is like NVIDIA Jetson or empowered, and you can actually train your models anywhere you want if you want to continuously develop and extend the models. If you're that kind of the person, that could be possible. This functionality that I talk about is not there yet. This is not what we built, but this is just like my imagination of what can be done else via the power of GPUs. The thing that we did was porting the Neural Amp Modeler core project and repository, again, which is open source. And we turned this using our GPU audio SDK that my partner, Alexander, will share a few more lines about how we exactly did what the SDK is made of, what are the results, and so on and so forth. So we did that thing and we turned the inference part working on the GPUs. And the main reason for that was because GPUs are extremely powerful and everyone have these GPUs as part of laptops. Right now, I'm speaking to you in my M4 MacBook Pro M4 Max, which is like incredibly powerful device. I here have NVIDIA RTX 4090 based, and now it's like 5000 series already available. I watched the new laptops working at the CES show back in Las Vegas a week ago. It was like they started to be that thin, like 2 times thinner, or like 30–50% thinner than the last generation, yet more powerful, which is again incredible. And the reason why we empower this is because GPUs are incredibly powerful, so you can host larger models with more thicker layers. And for the programmers, it means regardless on what kind of the tensor operators your model is made of, you can always go for bigger and bigger model and make it running real time. And you can host as many tracks as you want. So that means, imagine you want to use, again, embedded NVIDIA Jetson Orin device, which is like now $250 per hardware kit, like development kit. And in my understanding, the production unit can be as low as $49. I'm just speculating. I'm not NVIDIA, I'm not representing NVIDIA. Just call NVIDIA and ask the price. But the point is, you can run this thing on this tiny ARM-based CPU plus a GPU device, and you can empower the entire guitar music band, let's say 8 people, and run all of these effects in chains, run distortion, delays, and all that thing. And you can extend some of the neural powered models from a very few knobs that currently exists as a part of neural amp modeler plugin to something else. So you can add more and more layers. You can add more knobs to control something else. And you can extend from just the basic functionality of the plugin and add some more effects in between if you leverage the power of GPU. So without taxing the CPU, always running this on the low latency and so on. So we've done all of it because of that goal. And we also, just let me share really quick my screen really quick. So we've been also presenting this during the ADC show. Hopefully you can see my screen and my slides. So this presentation is already available for Audio Developers Conference members. And here we basically explained the whole diagram, how the NAM works, DSP-wise, and what kind part of the neural amp modeler, the core project and repository that we been overriding the behavior of. We just replaced one part of this project and we added if else. And if a GPU version go here, and then there goes our implementation. We also explain how our SDK worked very briefly. We showcased the code, how to make it work. We also told a bit of a story about the different models, how they are different quality-wise, how they are different implementation-wise, and computational complexity-wise. We picked up back then WaveNet, if I'm not mistaken. Now we support them all. So our implementation already have also LSTM included. So for that purpose, we implemented our own linear algebra library, Python Torch, and the backend behind the mathematical library, let's say Triton C or TensorRT. Obviously, there are closed source project, right? And like provided by NVIDIA and the other companies. And what's more importantly, they don't work with latencies that we talked about and demoed during the ADC. So nothing like 2 millisecond, 1 millisecond latency, nothing like that. Also available at scale, nothing like that is possible if you go natively with TensorRT, or if you go through Python, then get things compiled by TensorRT or any other backend such as Triton C. So thus, we had to implement our own math library that works with our technology, which is low latency scheduler that we already been presenting for quite a while for the community. This is basically a few more details on how these neural networks work, and then we explained how this thing worked, and then we talked about results. So just one tiny bit disclaimer about the results, right? We didn't aim to run like 100 or 300 or 500 of plugin instances real time, right? But we have to somehow showcase what is the performance gain, right? And the reason why we show the performance gain and how ultimately GPUs are better than the CPUs, as you can see in this slide, is to explain to the developers that now with limitless power that you have available, you can further extend your neural network model, right? So you can add, throw more layers and provide more level of the control. And then you can expose this functionality to your customers, to the users, so they can actually run more complex effects real time with more instances, as long as they need, without taxing the CPU, without sacrificing the latency and everything else. So some of the results for NVIDIA RTX 4090, for M2 Max mentioned here, and that's it. This thing is available still on our Jupyter notebook. So please feel free to sign up with these credentials to have access to our neural audio workshop, where we basically explain how to empower neural amp modeler's core repository, how we exactly ported this using our library, how you can alter this implementation so you can extend or replace with your own neural network design, and you can do whatever you want to do there. And yeah, we will make this work later on, and we will, hold on, let me get back to Zoom somewhere. Help me, I'm not good guy. I'm not proficient in where to stop. There we go. Share. I'm not sharing the screen anymore, right?
You're still
I'm
sharing
not.
it. I can stop it from over here though, if you'd like.
Yeah, thank you. Yeah, I'm super confused with Zoom. I always use Google Meet. As my spouse is a Googler, I'm obliged. This is only half joke, and she doesn't hold a pistol right into my head. So yeah, so this is our implementation. This is available, and we at GP Audio, we want to make this also available for the community by releasing our SDK as binaries, and also as binaries of the neural amp GPU version, so everyone can actually make it running under Windows 53 and Mac OS 6, and also in the form of the open source project, where you can again leverage the power of our library and rewrite your own neural network just in the classic CUDA style C++ code. So anyone who deal with parallel programming at like intermediate level, and everyone who understands how the neural network works, even on the Python world, they would be able to write in the C++ just by leveraging our library. And I would like to invite Alexander to tell a little bit more about the technical detail, how it can be done, and when our SDK will be available. Alexander?
Yes, thank you, Alex. So let me start from quickly talking about the CPU versus GPU. So why do we want to bring the GPU in the pro audio processing at all? Well, basically, the modern GPUs are, of course, the devices with the immense compute power, which can bring the immense throughput to the pro audio use cases. But when used through the generic APIs, so to say, like OpenCL or CUDA, usually people find out that you cannot achieve latencies which are considered real time in the pro audio world. However, our SDK, our platform, our scheduler that Sasha mentioned previously unlocks this possibility. So, and what is the difference from the programmer's perspective, so to say? So, modern CPUs are very smart, so to say. And usually, when we are optimizing a CPU code, what are we doing? So, of course, yes, we have SIMD instructions, but apart from that, all we can do is try to write our code in such a way that we hope that we wouldn't have cache misses too often. We don't have to go to directly to the RAM too often, and we hope that the branch prediction will work pretty well on the CPU, and so on and so forth. So modern CPU is, so to say, a very smart black box. And in contrast, when we are writing code for GPU, yes, it has an immense amount of ALU cores. It has very fast shared memory. It has very fast global memory. But on the contrast with the CPU, GPU are rather simple, and all those things can and should be done by the developer. But because of this, the performance that can be gained on GPU is unparalleled. What do I mean for that? practical example, when obviously, because we are talking about NUM, about neural AMP modeler, we are talking about machine learning, there is quite a lot of matrix operations. So we have to multiply matrices, etc., etc. And to be able to do it very efficiently on GPU, this was, in my opinion, one of the main technical challenges for us when we were porting NUM core to the GPU, was to write our matrix library in such a way that it will work efficiently for all the matrix sizes that are actually used, for example, in the WaveNet model, which is kind of difficult task because different models has different sizes. But anyway, we can say that some of them are used more than the others, and then the thing that we did in the end, at least for some of the models, at least some of the matrix sizes, sorry, is that we actually created template specializations with the custom memory layouts for the specific matrix sizes, because we know exactly on each platform how much memory we have in a register file, how much memory, how much shared memory we have, etc., etc., and we can leverage that to gain this top level performance. So this is GPU versus CPU. Now some more details about the platform and what are we offering and what we are solving actually at the technology level, so to say. So first thing that Sasha already mentioned and I've already mentioned is that we bring millisecond and even sub-millisecond latencies to the audio processing workflows. That's a must. Without it, we just can't really talk about pro audio. The second thing that we do is that we provide a way to write the processor's code, the DSP code, the machine learning code, the math code, so to say, in a cross-platform way. What does this mean? So if I want to write now without the GPU audio, if I want to write a plugin, and for example, I want to target Windows, macOS, and maybe even Linux with the LV2 plugins. What do I need to do in order to achieve this? So if I want to target Windows, on Windows at least we have two major vendors, NVIDIA and AMD. So for NVIDIA, obviously, I would need to write a processor in CUDA. For AMD, directly, at least CUDA is not accessible, so either I will need to rewrite everything using the AMD HAP SDK or use something else. If I want to do the same thing on macOS, I will need to use, for example, Metal, and again, write another processor. If I want to do it on Linux, well, again, we have NVIDIA and AMD, so we have CUDA and HAP, but we have POSIX host side, POSIX operating system. So again, this processor will not be exactly the same. And this is one of the major problems that we are solving. We are introducing on the level of the SDK the subset, the common denominator of all of these technologies, and you can write your code processor once. And then through the GPU audio platform, you can compile the same code for macOS, for Windows NVIDIA, for Windows AMD, for Linux AMD, for Linux NVIDIA, and so on and so on and so on. And in practice, this is even worse than that, because on Windows you will have different versions of MSVC. You will have the different versions of CUDA. When NVIDIA will now release the 5000 series, there will be a new version of CUDA, which will be tied to the new version of MSVC. In Apple world, the Metal and Metal CPP versions are tied to the macOS versions. macOS versions are tied to the CLang versions. And I can go on and go on and go on, but I will just say that internally our compilation profile count is around 160, because the Cartesian product of all these things, it just results in an immense support matrix, and we do all of that, and we can do even more. As Sasha briefly mentioned, we want to bring some of our functionalities to the Jetson devices and so on and so on. It's all possible for us. And that's another thing that we are providing to the GPU audio user. The next thing is what we call DSP library. But after the neural amp modeler, we probably should somehow rename it, because now it's not only consists of the classic DSP. Now we also have matrix separations, linear algebra, so it grew in scope. But generally, we provide a library of primitives which are ready to be used, and there are a lot of them. Basically, things that are needed to run the WaveNet, so matrices, vectors, multiplications, dot products, etc., etc. Classic DSP, AER filters, FIR filters, partition convolution, delay lines, FFTs, and so on and so on and so on. So we provide the DSP library, which is ready to be used to just construct a product from everything that we already have. But we are absolutely not limiting the user to the primitives that we developed. Everyone can develop their own primitives using the same SDK that we are using.
Right.
So you wanted to say something, Sasha?
Yeah, I just want to say yes. So we want to encourage everyone in the space. People who built on the top of the neural amp modeler, now is the way to breach your dream functionality with the power that is now unlocked. And this is the exact purpose why we have done this implementation. We incorporated in the form of the workshop, this workshop, and the repository with the implementation that utilizes our SDK is available at the slides that I revealed today. And also it will be available with our SDK release. So the entire workshop itself, the way you can go through and read through the material and understand the things and just to build things yourself, or just take the binaries and make things work the easier way, like you don't need to build from source. And you can now, you don't need to think over how big your neural network is, and you can run things that nobody can, and you can just imagine you're taking this neural amp modeler with a few knobs available there, and then you just add the effects chain, and within the effects chain you add like delays, distortion, all that kind of stuff that powered as a software that you can you're free to put it in the form of the plugin and run under Mac OS X for GPUs. By the way, Mac single GPU system, which was quite a magical trick to make it work on the single GPU system that empowers everything, all the graphics, all the operating system. It's different in comparison with Windows case that I have like embedded GPU and discrete one. And you can have this software powered on anything, including you can have it powered by NVIDIA Jetson. This will require some additional stuff because it's ARM-based system. So you will deal with ARM-based toolchain, which is a little bit tricky, but it's possible under Ubuntu. They have Linux Jetpack, so-called Jetpack packages that will bring Ubuntu 22.04 and even 24.04 and everything as a tool chain for you. So you can then use this tiny computer and you can use this hardware kit to build, I don't know, like any kind of enclosure on the top. It's extremely powerful. You can embed like a display, touch screen, a limitless number of channels, like real world channels and ports, and you can connect as many inputs, outputs as you need, and you can do something that big guitar amplifier makers that build this stuff that costs like 15, $20, $100. You can do things way beyond that, and all of it neural power. So that's the way you can alter that, and you can use our prepared template project just right away. So you can have our matrix .h source file where you basically have all of the math included into your project, and you can override our template project and build your neural network right away. And then you can expose those parameters in plugin side of neural amp modeler, and all you need is just alter the GUI. So you can start drafting your own product just right away. So it is as easy as it is. And as Alex mentioned, we provide this entire intermediate cross-platform layer. So we get rid of all of the thing underneath. And believe me, this is a lot of the stuff we do there. So Alex and Steve, I would like to invite you to like share any functionality, use cases, ideas that you might have in your mind. You can share with the audience how exactly they can leverage the power of the GPU, what else could be built. And then I would like to invite Josh to continue with our today's episode.
Yeah, I mean, one of the things that I think is, worth repeating, just as a kind of high level background is that, GPUs have been making, considerable steps in what they can achieve, so there's been, kind of for a long time, the sort of like news headlines about we're reaching the end of Moore's law, or the computers aren't going to be able to go much faster. The amount of scale that we've seen, this style of chip, uh, continue to make, since that sort of thing started popping up more and more. It really just kind of like highlights that you can be smarter about how you're doing how you're using silicon and doing compute. And so, I think that's it's a really exciting place to be for you guys, is to be kind of taking advantage of that, as that becomes increasingly ubiquitous in the sort of like compute that people have to work with, that that this is sitting there to help them kind of build with it.
Right. So I'm not sure if the audience is able to see our chat, but I just shared this link to the NVIDIA Jetson Super Dev Kit. It's it's a platform developed by NVIDIA. This is probably the #1 and only choice for folks that want to leverage GPU audio SDK and to go embedded into embedded world. As I mentioned, it's $249 kit. Should become available soon. There's a $500 to $600 and to a couple of $1,000 another hardware kit for the same chip architecture, but a different version of that can have up to 64 gigs of RAM memory that is shared between the CPU and GPU. That's like plenty. I don't know what you can do there with such a memory, but I believe a lot. This Super Dev Kit is like rather Orin Nana version, which is only 4 gigs of RAM, and I believe this is still plenty. This is plenty for any kind of the functionality that you guys want to run using GPUs. And by the way, whenever you deal with neural amp modeler or with the functionality that you have in your mind, you don't need to do like to rewrite your code in parallel utilizing our SDK. You just need to profile your entire application stack, like the process block call, see the profiling report, and just to see, okay, I have a few functions that utilizes 30 to 50% of the CPU usage, and I want to pour this thing on the GPU. This is the way you do the work, and you pour just like 5 to 10% of the code of the processing call stack maximum, utilizing our GPU audio library, and you keep the rest. So you don't rewrite your full code. And as we showcased how exactly to overwrite a NAM core project, we just leveraged one part of the SDK to replace the NAM core and to make it running on the GPU. The same will be valid for any kind of functionality that you want to run on NVIDIA Jetson or on your laptop or anywhere else. I believe the production version of the Jetson or Inanna could be as low as $49 if you will make a bulk order from NVIDIA. Again, I'm not representing NVIDIA. I have no idea. I'm speculating. I'm just indicating and highlighting you some of the possibilities what you can do. I think somewhere between $49 to $99 for the entire ARM-based CPU, GPU, memory, storage, everything is huge. I mean, not the price, it's not expensive, it's affordable. It's huge opportunity for the developers to bring something that has a extreme potential, extremely strong potential in comparison to what exists on the market, whether it's a neural DSP or like, I don't know, Gibson, Fender, whatever. Feel free to utilize Neural Amp Modeler, open source, and GPU audio to build awesome stuff. Thank you.
All right. Thank you so much, Sasha. Just going to turn it over to the audience for any questions. In the meantime, I put the link to the SDK in the chat for anybody who's curious. There is one question from Colin McRae who asks, what are the main limitations or roadblocks with this new method?
That's a good question. Alex, do you see from the programmer standpoint? I believe I can answer very quickly, and then I'll let my partner Alex to tell more detail. I think the number one roadblock is still you need to understand how parallel programming works, like in general, regardless on the architecture difference, whether it's parallel programming using CPUs or GPUs, SIMD, or any other approaches and architectures. You still need to understand how to write multiple thread application and how to sync threads, right? GPUs, S architecture, SIMD, they different from the CPU multi-threading approach because they use barrier synchronization. So you need to learn what the barrier synchronization is, how it's different, why it works on the GPUs better than anywhere alternatively else. This is one thing. Another roadblock is that you still need to at least be basic level proficient, somewhat proficient at CUDA C++ style programming. That means you need to understand how to write the host side code, the device side code, how to prepare data and send data to the device, and to learn a few primitives starting with the barrier synchronization, when to call sync threads, which is barrier synchronization call of CUDA. We have the same functionality. We keep this functionality behaving the same way, and it has different underneath implementations for multiple targets, operating systems, and devices and so on. So you call sync threads in C++ code to synchronize all the threads whenever you I don't know, filter the signal, or you want to multiple two vectors and so on. And you don't expose any implementation for all of these multiple targets, as Sasha was saying. You also need to understand how the memory hierarchy look like. on the GPU side, what's the global memory. It's a little bit slower than the faster cache that is on device on chip. How to use this cache whenever you need, how to read, write cache, right? You also need to be somewhat proficient at the DSP level. Well, if you're creating the product and you want to, let's say, add some distortion, and then you want to implement multi-band equalizer, you want to implement shelf filters, big filters, and so on and so forth. If you want to implement this functionality, you need to be proficient at the DSP both and somewhat parallel programming. You don't need to design those DSP primitives, GPU implementations of these DSP primitives. As Alex was saying, we have the entire library of prepared functionalities for you. So you don't run to DSP cookbook and implement fast Fourier transform of Cooley-Tukey implementation. That's definitely, you don't need to understand how to implement that thing. You just call FFT and it works the same way for a CPU as for a GPU, right? And this is, we guarantee you the precision and the result in comparison with GPU and CPU and GPU version. So it's IE 754 compliant, standard compliant. These probably are the only roadblocks, but I'll let Alex to tell if he sees more than me.
Yeah, you covered pretty well from the programmer's standpoint view. But there are also things that can be considered roadblocks or challenges for the platform. So first thing that I wanted to mention that kind of limits us is the current DAW sync interface when calling the plugins. Because when we want to achieve huge performance with the GPU, we can do this in two ways. We can create some, I don't know, singular product like a huge synthesizer or something, which just can't run in real time on CPU at all. And then utilizing the GPU acceleration, it just can be possible for the first time in history, so to say. Or we can accelerate the existing plugins and try to increase the throughput, for example, amount of tracks that a host session can handle, or amount of channels, or both. But when we were doing our testing, we were surprised that most of the currently used DAWs, they are not handling very well the track count more than 100 tracks, for example. More so if you will add a few plugins into a fixed chain on each channel. And this is not a limitation of the GPU. Actually, this is the limitation of how the mixing engine of DAWs work, and that they do not consider that some of the processing work can be done outside of the GPU. This is one challenge that we are constantly fighting with. The second one is that many of the classic DSP algorithms can be considered sequential. For example, IAR filter, because it has recursion, it is sequential how we can port it on GPU. But actually, there are things like, for example, state space representation, and then we can achieve at least the fourth thread concurrency, and so on and so forth. But as Sasha T mentioned, you don't need, and you probably don't want to port everything on GPU. You just want to pinpoint those parts that matter. That's exactly what we actually did with the NAM, because in the NAM there is a tone stack, which is a I believe free band equalizer, but it's trivial. Why do we want to do it on the GPU? There is a noise gate, but again, it's trivial. So yeah, We just ported the num core because this is where the magic happens, including this introduction of the CPU load, because magic isn't free, so to say. The third challenge what that I wanted to mention is what to do with the customer base without the GPU, at least without the discrete GPU. But again, this is really not a problem, because if you are we find out that our partners are in one of the two positions. First one is then they already have the CPU product they want to port to the GPU. They already have the CPU code as a production ready product or as a prototype. So then we have ability to basically implement the enable GPU acceleration button in an already existing product. And you don't actually lose any customer base, you potentially gain more customers. And the second one, like with one of our other partners, they came to us because the product that they had in mind cannot be run on CPU in real time at all. So again, win-win situation, so to say.
Right.
All right. So I think that's all the questions that we have from the community. One question that I had very quickly was, do you have any plans to make this more user-friendly, or do you have a roadmap for making that more user-friendly where they won't need to work with these low-level SDKs? And do you have any ideas on what that roadmap might be looking like and when you'd release something that was a little bit more higher level with some abstractions?
From my perspective, definitely. We would want and we would love to do so. Basically, our current plan is to release the first public version of the SDK in about a month. And from that moment, we would want to gather as much feedback from the SDK users as possible, because for us, as we are doing this for almost a decade, it can be hard to imply what are the most difficult parts in using our SDK. So the first thing that I want to do is to gather the feedback, basically.
Yeah, makes sense.
And from my perspective, I would love to add one moment. So yes, as Alex mentioned, we want to release the SDK and we want to provide more examples. And we also want to hear the feedback, whether it's hard to use or something doesn't work, and to fix that for the community. We wanted to provide as many ready to go recipes for the community as possible. I mentioned one already. We incorporated this whole thing in the form of the C++ team project. So you can, again, you can take any neural network and model and implement it your own, expose parameters, and just make it work on the GPU right away. So you don't need to deal with like integration part, neither with our SDK, just override the function that's already there and expose whatever float parameters you want to be exposed. That's pretty much it. It's like ready to go. One thing worth mentioning, I know machine learning engineers live in the different world, in the Python world. And Python is beautiful, yet I hate it. That's not like my personal biased opinion. Python has its own advantages and limitations, right? And there are reasons why huge corporations, multi-trillion dollars such as NVIDIA and the others, they have very smart people paid by like hundreds and millions of dollars every single year that maintain this TensorRT and all of the libraries running by it and all of the translation layers and integration and infrastructure that's now being utilized by Python community, from Python world when utilizing PyTorch and the other libraries. So there's a huge reason behind that. We're a tiny, small startup, and we don't have trillions, neither we have like anything in comparison in terms of resource, right? So enabling real-time audio inference and all that stuff on the Python world is a huge thing, even for us. So one step forward towards this direction was to make things work in under C++. That, as I mentioned, even to make it in the 3 weeks, I am the dumbest person in my company, so I'm just the talking head. I'm describing myself as a talking head, but the other people, like Marcos, like Alex, and Daniel, and the other folks that actually implemented this GPU version, they understand how this works. And to bring this in the C++ world, it was a tremendous effort that they made. And we have plans to make this thing running under Python world, where you basically replace some of the functionality that you want to run on the GPU real time with our implementation. So let's say you replace some of the PyTorch calls with our library included into your project calls, and this will just turn things on the GPU side. You need to take care of data transfers for quite a bit, but if you do that, you would be able to run this thing under the Python world. This is our future plans, not yet announced when such a functionality will be available. We'll see how this thing will go under C++ world, and if there is a demand, we will be happy to make it work under Python.
Amazing. Thank you so much, Sasha, Alexander, and Steve. Fantastic presentation.
Pleasure.
Love to see this brave dive into a whole new realm. You know, a lot of stuff happening on the GPU right now. Makes sense that people explore ways to use it.
Thanks, Josh. Thanks, community. And feel free to dive into our Jupyter Notebook now, today. And just in 1 month, the whole SDK will be publicly available on the GitHub. You would be able to read through all of the examples, to post, submit some issues if you will find any, and to provide us a feedback. So we will wrap again and get rid of the unnecessary things and wrap it nicely so it will be easier to go with, to use. Thank you.
Fantastic.
Cheers.
Great. Thank you so much, Sasha. So now what we're going to do is we're going to go ahead and shift gears to our second talk, who is coming from Domenico Cipriani in Italy, and he's from the Pharo Association. And this talk is about Fausto, which is for prototyping DSP. And I'll just read his abstract very quickly to help give you an idea of what this talk is about. Learn how Phausto, a Pharo-based library and API, makes DSP programming accessible through Pharo's pure object-oriented model, minimal syntax, dynamic live environment. By harnessing the power of an embedded Faust compiler, Phausto provides full access to Faust's extensive libraries and exporters, enabling the rapid development of audio tools. We'll focus on its C major exporter, demonstrating how to create a plugin and use it within a DAW using the C major wrapper plugin. Designed for educational purposes, Phausto empowers sound artists, producers, and beginners, making advanced synthesizers and effects design quick and short. And with that being said, I'm going to pass the mic over to Domenico. Take it away.
Hey, hi, Josh. Thanks a lot for having me here. And I've been learning a lot of stuff through the Audio Programmer channel, so I'm very happy to be here. Also, I have the book here. I learned a lot of stuff. So it's a pleasure to be here and to show the Phausto and all this framework to our follower on the channel. I want to thank also the Pharo Association for sponsoring my work. And then I want to thank all the Ref team in Lille for helping me with Pharo and Phausto, and the Faust team for helping me in the stuff, and also Cesar Ferrari at Cmajor for making this really happen, because it was his final touch, as we will see, for having this C major export. Okay. First of all, I would like to introduce a little bit myself and how I arrived to conceive Fausto, and I will discuss a little bit the technology used and their history. Okay. So I've been producing music, DJing, and performing live for almost 20 years. Especially with machine, so with hardware and with vinyl. I got a degree in electronic music production at SAE Barcelona like 20 years ago. And then I studied linguistics at the university. So I'm not a programmer. I mean, I'm not studying computer science at the university, but I learned by myself. And let's go with the slides. So screen two. Yeah. Okay, let's go to the slide. This is Pharo. Okay. So as an introduction, I would say language as C++, Faust, and also C major, they are extremely powerful, but they are also very intimidating for beginners. And well, Faust and C major are simpler, but still they are complex for people with little computer literacy, it could be musician or producer or sound artist. Okay. Using Fausto together with Cmajor bridges this gap and make it much simpler and much faster. What is Faust? As you were telling before starting my introduction, Faust is a multi-platform library and API for Pharo that is for writing DSP. It works on Linux, on Windows, on Mac OS X. It's quite lightweight. All the library is less than 10 megabytes. Fausto was developed with three main goals. It was to allow sound artists and musicians to program synthesizers easily with Smalltalk, with Pharo, and also to teach DSP programming to very beginners, and then to offer a platform for prototyping and use this DSP thanks to the C major and also with the C++ exporter. Then, of course, it was also to enrich the Pharo environment with sound, but today we are going to focus on point two, so writing this DSP code and plugins. I began programming in 2017, so not so many years ago, thanks to Christian Vogel and symbolic sound schema. We will see in a while what is schema. Then I've been developing Koipu in Pharo for programming music on the fly in 2020, and this was my first experience with Pharo. Also in 2020, I started to develop audio plugins with a company called Soft Computing that we founded with my friend DJ House of Unknown to the Unknown, and with using Juice, it was made possible for me to make the plugins that we did. And since April 2, 2024, I'm sponsored by the Pharo Association for my work with Fausto. A few stuff about symbolic sound schema. So symbolic sound schema is made by Carla Scaletti and Kurt Ebel at Urbana-Champaign. It is a IDE and computer language that is made for audio, for sound design and sound performance. The Smalltalk code inside schema has to be compiled on an external DSP. The first one was called Capybara, then we have the Pacarana, then we have the Pacamara Ristretto now. For somebody, it's called the Holy Grail of sound design, as it is extremely powerful. It is also extremely creative, and as it is in Smalltalk, it is very easy to learn. So Smalltalk was the first language that I learned with the book on schema, and I got in love with Smalltalk. And Smalltalk is so easy because when it was conceived in the 70s by a group of researchers, including Alan Kay, Dan Ingalls, and Dalen Goldberg, and more, it was a language that was conceived for teaching programming to children. And this concept of Smalltalk introduced like graphical user interface, model view controller, and a live programming environment that we also have in Pharo. Okay, so Pharo also is a pure object-oriented language that comes with a platform-independent IDE, so it works on Windows, Mac, and Linux, again, with very small requirements, and there is a lot of retrocompatibility, so it goes on ARM, it goes on Intel, it goes on very different OS. Pharo comes from a fork of Squeak created by Stefan Ducasse and Marcus Denker, and it was thought as going beyond the original of ideas of Smalltalk, so to make a real world language. And now it's developed by an international community and maintained by the Pharo Consortium. It has a non-viral MIT license, so it can be used everywhere. And it comes with integrated Git support and with an integrated framework for S-unit tests. So with a lot of stuff, we will not have, I think, time to see a lot of about Pharo, but there are a lot of tutorials, a lot of videos online to learn about Pharo, a lot of books. I will give you a quick look of how Pharo looks like. This is Pharo 12. Okay, so on the top left, we have Iceberg, that is for committing and pushing your code, so for versioning. Then we have the playground, when you can write your code and evaluate your code in real time. Then on the right, we have the inspector that is to inspect objects and to debug codes in real time. And then we have the class browser, where we have our classes and where we define our methods. So let's say in the playground, you sketch your code, but then your code goes inside actually packages and classes for reuse, okay? The syntax of Pharo fit a postcard, okay? It's very concise, it's very easy to learn. We have 6 rules, like as you can see there. Everything is an object, every class has a superclass, everything happens by sending messages. Method lookup follows inheritance chain, and classes are objects too, and they follow the same rules. And then there are the precedence rules are very easy also. So ordinary message first, binary messages then, and then keyword messages. When there are multiple messages with the same precedence, they go from left to right. So for example, 3 plus 5 times 4 would be like 32. And for those who don't know Faust is a purely functional programming language. So it's like on the other side of the programming language spectrum, respect of Pharo, but is considered the state of the art in the research and development of DSP algorithms. There is a lot of work in filters, physical model, reverbs, effect analyzers. So with Faust, it comes a very extensive standard library. I really love the sound of Faust, especially for this quality. And Faust then compiles to C++. You can use it on an online editor, or you can use it for command line. But what was also very good about Faust is that its architecture and its CBox API was enabled like to embed it on Pharo quite easily, let's say. Here is a brief look at what comes with Faust. A lot of things, a lot of oscillators, low frequency oscillator, impulse train, waveguide, resonator, many filter, a different collection of linear and exponential envelope generators, tons of effects, a lot of first-class reverbs, physical modeling, instruments, and low-level stuff, analysis tool, dynamic processor. So we have everything. And then why Cmajor? Well, I like a lot of Cmajor, and it was easy to export the DSP code from Faust, so from Phausto to Cmajor. And it is really easy to use the Cmajor patch that is created, just loading this patch in the Cmajor plugin that is given by the Cmajor team. So as we will see later, it's really easy to use the Cmajor patch inside the VST wrapper. And I think this is something that can really speed up the development of plugins and also the use of plugin, especially if you think for like artists and producer. If you like, for example, you want to have your own synthesizer, something maybe not so complex, but you have ideas for doing that, you can just plug what you got in Faust and export it to Cmajor. So there are many resources to learn Pharo. There is a massive online open course that is around 7 weeks at slow speed, I would say. And then there is also an advanced course with 10 modules to learn proper object-oriented programming design, so like design pattern, and if you need to write proper code. Also, you can use Pharo is reflective, and you can inspect everything, so you can learn from inside Pharo because you can look and read every method and every class. And then there are also a lot of free books. To install Fausto, you have first to download the Pharo Lancer. That is a tool that is used to launch Pharo images. Then there is this GitHub page where you have to download this libraries bundle. That is a folder that contains the compiled dynamic engine, the lib Faust, and in case for Windows and for Linux also port audio, while for Mac we are using core audio for the sound. And then we just have to copy this command on the playground. That is where we play with our code in Pharo, and it will load everything we need. How we learn Fausto then? Well, we can open a playground and evaluate master loop Go, and it will open a series of tutorials. Now we have 7 tutorials covering the very basics, but we are working on more. And also, we kept the semantics of Fausto very close with Faust, and we choose to have the same name for the parameters as in Faust. So if you are familiar with Faust, we will also learn easily Fausto. And also, like, we have all support for parallel, sequential, split, and merge composition. And the idea behind Fausto is not to replace Faust or to replace Cmajor, but is thought and conceived like an entry point for people with little computer literacy or with little DSP programming experience to get familiar with how this work. And then there are many things that you can do with Fausto. Maybe there are some things that you will have to do with Cmajor in terms also maybe of interface, but all goes together. Okay, so the concept of Fausto is a little bit the concept of modular programming. So we connect unit generators. These unit generators are come from the standard library of Faust. So Faust is a functional language. There is no object, there is no class. We implement this function like the oscillator, the rebus, the filter as classes, using also like inheritance and trying to organize the code in different packages and superclasses. The idea of the organization of the unit generator comes a little bit from the Chuck programming language. That is a high-level programming language, object-oriented, very fun to use, with a very good sound. So we also borrow the Chuck operator to connect the unit generators together. So when you connect unit generators with the Chuck operator, it knows what to do. So if you connect an oscillator with an envelope, for example, it knows that you are multiplying the output of the oscillator for the envelope. While if you connect it to a filter, it's going to the input of the filter. Okay. So we make this chain of unigenerator, then we send the message as DSP. We also send a message stereo if we want to do a stereo DSP instead of a mono. And then the DSP is compiled. We can then initialize it to our audio backend, port audio, core audio, and then we start it and we hear the sound. This was basic, okay? This oscillator with an envelope, a filter, a resonant filter, and a SAT reverb that is a JC version of the JC reverb. We connect them together, and then if we send that, we have a message display UI to see an UI in Pharo and to play with the sound. But then we have this method called create Cmajor MIDI patch name, and this creates a folder inside the document folder. It creates first a Cmajor patches folder if it doesn't exist, and then it creates a folder with the name of the synth and with 3 files. One is the actual Cmajor file, one is the Cmajor patch, and one is the poly wrapper that manages the polyphony of the synth. Also, if we don't want to create an instrument, but we want to create an effect, we send the message create Cmajor effects patch name instead of MIDI. This was, you can see the different, like the code in Phausto and the code in Faust. The code in Faust is kind of much more verbose because in Faust you have to define UI parameter if you want to control in real time the parameters of your DSP, and also if you want to see the UI. While in Phausto, everything comes already with a UI defined. So the only thing you have to do is to define a gate parameter, a FRAC parameter, and a gain parameter to have a MIDI synthesizer. This is just the beginning of the Cmajor code. Of course, this is not the Cmajor code that you will write for the same synthesizer, but it is like the exported version from Faust, so it's much more verbose. Then once you have the Cmajor patch, you open the Cmajor plugin, you drag and drop the Cmajor patch file, and you have a synthesizer or effect with a generic UI. You can write your UI in JavaScript. I think there was also here, there was some talk about making the UI in Cmajor with JavaScript, and that's almost everything for the slides. Now we will try to see some code together live and just talking about what we have next. So now we have like ported 65% of the huge library of Faust. We want to port everything you got in Faust. We want also to implement some kind of auto smoothing because now the parameters are not smoothed, so it can sometimes give to some kind of cracklings. Also, we are going to implement more toolkit object. This toolkit is conceived to be some kind of higher level unigenerators built on the top of what is offered by Faust, like to select files, to handle envelope, or to make filter envelopes, or like effects with dry wet control. So to make easier, the idea is the user of Phausto can have a good library of high-level object to compose their DSP. But of course, they also can write low-level stuff just with mathematical operators. Of course, this comes with a question: why should I re-implement the wheel? Why should I implement the CZ oscillator if the people of Faust did it so well? Well, there's a question. And then here you can see we have 2 examples of the UI made in Pharo with Block, that is a UI infrastructure, low level, very nice and very powerful. On the left, we have the standard UI that it comes just sending the message display UI to a DSP. And on the right, you have a very nice TB free of free clone made by an intern, Janesh. It looks really nice. And the idea is to have some kind of exporting this UI to a JavaScript file, so we can have a custom UI for every Cmajor patch we have created. Also, we have to work on more video tutorials and a booklet on Phausto, like a guide. There is a short workshop I did at the Faust conference online. I will put the link. And then as soft computing, we want to make available the Cmajor wrapper on our Bandcamp page, and then start developing a series of low-cost scenes and effects, or also something for free, just to encourage sound artists and musicians to use Cmajor patches, because we really think that this probably is the future of the developing instrument and effects, at least especially for not people that are not like developers for their job. And that's all for the introduction. Let's say that's all for the slides. Now you can see Pharo. This is the Pharo environment. We have the playground. We can open different playground. We can evaluate our code. Okay. So for example, here we can have, I made this example. We have two oscillators, one for the left channel, one for the right channel. We don't need the stereo here. And then every unit generator has a set of setter, and this setter, depending of the argument of the method, if it is a symbol, it changes the label on the UI. If it is a number, it changes the initial value. If it is another unit generator, it assigns this unit generator to that parameter. Okay. And that, for example, we can go, what happened? We can go to the class and opening a class browser with command P and go here and see the comment, what it is. It is attack release exponential envelope generator, and we can see that it has a sustained value, okay? The initial value, the minimum value, and it is a subclass of envelope, and envelope also has attack and release and a trigger to trigger the envelope, of course. So we can evaluate this. We can command D, evaluate this, then connect the left oscillator to the left envelope, connect the right with the right one, and then use the parallel. We keep the parallel combination with comma, as in Faust. Make a DSP, we initialize, we start, we display the UI. The UI comes. Now I have changed a little bit my inputs to hear the sound. Let's.
Oh, we can't hear you, Domenico. Ever since you played the patch, I think.
You heard the patch, right?
Yeah.
Okay, so once we can test the patch with the UI, we can play it, we can connect a MIDI keyboard and use the MIDI keyboard to play it or to control the parameters. And then we create this MIDI patch we create a Cmajor patch. In this case, it's a MIDI patch, and it will be on our document folder. It's here, it tells you, and we have all the file. And then, for example, in Ableton Live, we can have like the Cmajor plugin that's using Ableton Live because everybody knows it. Okay, and then we can take the C major patch. Okay, now we have an error. For example, we didn't define the gain. We always have to define gate, frequency, and gain to gate, frac, and gain. So here, for example, I can say like that we want a gain. Okay, so in Pharo we are cascading message. So here, for example, we create an envelope, we create the other envelope. Then we want to create this new square oscillator with this label for the frequency, but we want also to change its level. All the unit generators, all the oscillators comes with a level control in Fausto by default. So we can just call this level control that is called U level. We give it the label gain. And this is semicolon is called the cascade operator. So we have like cascading messages. We are sending frac and then U level to there are two keywords messages. We can do the same for the other oscillator. So let's evaluate again. I'm missing a bracket. Okay. Okay. Evaluate again. Let's see if it works now. Okay. And you see the patch is generated, and there is this kind of hot reloading of the C major plugin that is super cool. So when you change the Fausto code and you export the code, it's reloading if you change something. And now we can just play some MIDI notes. Just see it goes. It's clear.
You went silent again. Yeah, we heard the patch, but now your mic has come out.
Okay.
There we go.
So it's all by my side. We got a very quick demo, but there are more things to see, and I'm open to questions. I stop sharing. How I stop sharing? Can you please stop the sharing, Josh?
Oh, you stopped it.
You stop it?
Yeah.
Okay, cool. Yeah.
Great. Is there anything else you'd like to say?
Not so many things. I mean, a lot of things, but I think to do a tutorial on Fausto, we need a little bit more time. Now it was a lot of information, but it was to give you an idea of what you can do and the motivation behind that. Also, yeah, maybe just a little thing, just another short thing. You know, even if you have like developed a plugin in C++ or Juice or whatever, and you know how to do it, then it's like half of the work, because if you want to share the plugin with somebody else, you have like to code sign, notarize, you have to do it for Windows and for Mac and for Linux. And like, so if you have a very like an instrument you want to share it with the world, share a C major patch is much easier.
Mm-hmm.
So this is one very good point about C major.
Yeah, absolutely. That's fantastic. Stefan Letts from the Faust team was in the chat a little bit earlier. Hopefully he's still hanging out. Looks really interesting. So what are the future plans for this?
Yeah, the future plans for, as I was saying, the future plans is to have everything of the Faust library, to have a way also to export the UI made with Pharo, because it's a lot easier to made, at least for me, but to make a UI with Pharo than to make it with JavaScript. So, but it will be an option, and of course to encourage people to use Cmajor, and so to use Phausto, and it goes all together. Then also, like there are other stuff like if you want to play sound files, maybe you have to work a little bit your Cmajor code. So maybe we should do some tutorial of step by step, making something in Phausto, then tuning the code in Cmajor, and stuff like that.
Yeah.
So the idea is to spread it more to the world.
That's awesome. Looks like we don't have any questions from the chat, so we'll go ahead and wrap this one up. Thank you so much,
Okay.
Domenico.
Thank you very much.
Yeah. Great. So we'll go ahead and wrap things up for now. Thanks for everybody who's joined in on the meetup. It was great to hear all these different perspectives and all this new groundbreaking technology on how to create amazing audio products and creations. So thank you to the GPU audio team. Thank you, Steve, and thank you, Domenico. Our next meetup is going to be on February 11th, and we will be making some announcements about who those guests will be soon. If you haven't joined our community already, be sure to come check us out. I think pretty much everybody in here is in our community on Discord. We have over 11,000 people all across the world, all different experience levels. So if you're interested in learning more about how to create your own audio plugins and audio products, your own DSP algorithms, please come join us. You can join us on theaudioprogrammer.com/community to join our Discord group. We also have some learning resources as well. Find out more about those on theaudioprogrammer.com. But for now, we will go ahead and let you go. So if there's nothing else, we'll go ahead and see you on February 11th. Hope everybody stays safe out there, and we will see you again soon. So take care.
Thanks, everyone, and cheers.
Thank you.
Bye-bye.
Thank you. Bye bye.